Okay, in this lecture, we're going to talk about pH, the scale, what it measures, and how we calculate a pH. First, let's briefly review this notion of H plus and OH concentrations for water, a neutral solution, or an acid or a base. We talked a lot in previous lectures about this water dissociation constant and how it equals, at room temperature at least, 1 times 10 to the negative 14. And this represents the concentration of H plus times the concentration of OH minus. Now, we know acids donate and create H plus. We know bases, one definition, Arrhenius, says they create OH minus. So it's no surprise that another definition more mathematical here is that if a solution is acidic, we're going to have more H plus, okay, than OH minus. If a solution is basic, we're going to have more OH minus than H plus. That stands to reason. But what's always going to be maintained here in these aqueous environments is Kw, right? It's always in equilibrium. This equilibrium value, 1 times 10 to the negative 14, is always maintained in an aqueous solution. Okay, at 25 degrees Celsius, it's 1 times 10 to the negative 14. That number might be different at other temperatures and will be. But at that specific temperature, the number is maintained. Okay, the reaction shifts left or right in that equilibrium establishment to preserve this equilibrium constant or this water dissociation constant. So for this acid in an aqueous environment, still 1 times 10 to the negative 14 is maintained. In this basic environment, it's aqueous, still 1 times 10 to the negative 14 is maintained. Okay, but you have to multiply these two things together to get this 1 times 10 to the negative 14. So in this basic solution where OH minus is much more, well, in a base, okay, that might mean that this is, 10 to the negative 5, and thus this is 10 to the negative 9. And those two things multiplied together maintain this 10 to the negative 14, okay? In acidic, right, this could be 10 to the minus 3, and this could be 10 to the minus 11, multiplied together, creating this 10 to the negative 14, okay? So in the basic scenario, there's more OH, 10 to the negative 5, than H plus. In the acidic, there's more H plus, 10 to the negative 3, compared to OH, 10 to the negative 11. Okay, so we can try a practice problem just to sort of nail this down. And you might come across a problem like this. An aqueous solution contains this molar of hydroxide ions at 25C. What is the concentration of hydrogen ions? Okay, and is the solution acidic, basic, or neutral? And here's where people trip up. I'll tell you in a second. You can pause the video here if you want to try it yourself. Otherwise, I'll work forward and solve it. Is the solution acidic, basic, or neutral? Well, just reading this and seeing hydroxide, right? This hydroxide here is OH minus. You're tempted to think, aha, there's OH minus around. It's basic, okay? But there's actually always OH minus around. It's a product of water. So exactly how much OH minus is around will affect whether it's acidic, basic, or neutral. So let's take a look at this. If there's OH minus in the amount of 1.8 times 10 to the negative 9 molar, and I also know it's an aqueous solution, so I know in an aqueous solution, this must be maintained 1.0 times 10 to the negative 14, and this is a representation of H plus times OH minus, where this OH minus is 1.8 times 10 to the negative 9 molar. That's the concentration. So I can solve this for H plus, divide both sides by this. So my H plus concentration here will be 5.6 times 10 to the negative 6 molar. And now we see that H plus is much greater than the amount of OH minus I have around, 1.8 times 10 to the negative 9. And so this clearly then is acidic because there's more H plus than OH minus. And so that should be the answer here. It's acidic, the concentration of hydrogen, 5.6 times 10 to the negative 6. Now, we can do math like this to express exactly how much H plus there is and exactly how acidic it is. But scientists like to make it a little bit easier. These are really, really tiny numbers, and, especially communicating with the public sometimes, you don't want really, really large or really, really small numbers. So is there something we can do to this value to make it more approachable, to talk about it more easily? And that's how we come up with pH. pH is a method of reporting the hydrogen ion concentration. Okay, so pH literally means, the little p means take the negative logarithm base 10 of, in this sense, H, the H plus concentration. All right, so in the previous example, you can take the negative log of 5.6 times 10 to the negative 6, right? This value we just did in the previous example, and you'd get a pH value of 5.3. Now, a couple things here. One, pH has no units. Okay, you don't write 5.3, molarity or 5.3 moles or 5.3 grams. No units. The pH is just 5.3. And we established on the previous slide that this H plus is more than the OH minus, assuming this water dissociation constant at 25C, so it was acidic. And so this pH value of 5.3 should be acidic. And it turns out that we'll say an acid is any pH below 7, base is any pH above 7. So previously we calculated for that one a pH of 5.3, that is acidic. Okay, so pH is this logarithmic scale. All right, so importantly here's our 5.3. Here it is. This is our answer right here. That's where it is on the scale. Somewhere, less acidic than black coffee because it's a lower pH. More acidic than milk, which is about 6.4. Much less acidic than pH. Okay. You have other things like bleach, household cleaners, pH of 13 or pH of 10. Baking soda is a base, pH of 9.5. Salt water is a pH of 8, so that's slightly basic. Okay, where these things would be very basic. Okay, milk, slightly acidic. Lemons, very acidic. Okay, and remember, not a good way to define acids and bases, but one we're sort of familiar with is that acids are sour, okay? Bases are bitter, right? But please don't go around tasting acids and bases, right? It's just something we're sort of familiar with. So lemon juice, very acidic. Grapefruit juice, very acidic. It tastes sour. That's one of the sort of telltale signs of an acid, right? But we're scientists, we want to quantify this in a much safer way. And so we calculate the concentration of H plus in these things, take the negative log, and that's our pH scale. Okay, note it is logarithmic. This is a common point of confusion in just science communication in the general public, right? It seems like, okay, black coffee is 5, lemon juice is 2. Those aren't that different, right? That's what you might say, but this is logarithmic, right? Which means every difference of 1 here is a factor of 10. So a difference of pH of 5 and pH of 3, well, pH of 4 is 10 times more than 5. pH of 3 is 100 times more than 5. And pH of 2 is 1,000 times more acidic than 5. Okay, so a lemon is 1,000 times more acidic. Okay, and that can be a confusing nature of logarithmic scales. Just be aware that pH is a logarithmic scale. Now, pH isn't the only negative log scale. It's certainly the most common, right? But that P in pH tells us to take the negative log of a quantity. We can also have pOH, exactly what it sounds like, negative log of the OH concentration. We can have pKW, negative log of KW. We can have pKAs. We haven't discussed this yet, but you can have acid dissociation constants and measure pKa, which would be a negative log of the Ka value. Okay? So all of these are other P systems that we'll come across in chemistry. Now, pH and pOH should be closely related. And they should be closely related because we know that they both come from concentrations of H plus and OH minus, and we know H plus and OH minus multiplied together, right? 1 times 10 to the negative 14, that's our Kw. So we can mathematically derive this relationship from this value. And so if we take the negative log of both sides here, we have a negative log of all of this. And remember, negative log x times y is the same as negative log x plus negative log y, right? That's just a property of logs. So when we take negative log of this left side, we get this. This is pH, negative log H plus. Remember that, okay, this H plus is kind of shorthand. It's more, formal to write H3O plus. H plus combined with water, it's in an aqueous solution. So these are sometimes interchangeably called the same thing, right? So negative log of H plus or negative log of H3O plus, that is our pH. This, of course, is our pOH. Negative log of this side would be our pKw, but negative log of 10 to the negative 14 is 14. And so we get this in the end, we get pH plus pOH is 14. Right? So if a lemon has pH of 2, it has a pOH of 12. And if you want to convert from pH to the hydronium concentration, it's 10 to the negative of the pH to get to the concentration of H plus or hydronium. Okay, so a lemon's hydronium or hydrogen ion concentration would be 10 to the negative 2 molar H plus. Likewise, it would have 10 to the negative 12 OH minus. And you can then see these two things multiplied together still maintain this 10 to the negative 14 water dissociation constant. Now, it's not always so easy to look at something and know whether it's acidic or basic, whether the pH is changing throughout a chemical reaction. And so we measure these things a lot of times with indicators or litmus paper that will change color when the pH is changing. And this comes from these compounds. For example, methyl red is one, right? That can bind to free H pluses or OH minuses that are floating around, and doing so causes a structural change in the molecule and rearranges it such that it interacts with light differently. And so methyl red is one of these indicator molecules that when it's below 4.5 pH, it's red, okay? But if the pH is raised through the addition of a base or something else, and now you have a lot more OH minus around and a lot less H plus than you previously did, okay? And so maybe the pH is now above 6. Well, now it turns yellow because of this structural rearrangement due to these different ions floating around that it's binding with. And in between 4.5 and 6, which is a pretty large range because remember that's a logarithmic scale, right? You have some of both types, red and yellow, around, and so the color change is kind of gradual for that methyl red, and thus that solution. Okay, so we can use these indicators to track pH changes, and there's a whole bunch of them. You can make a rainbow of different indicator molecules and a rainbow of different colors based on the pH. And you have litmus paper, which is really, really cheap and an easy way at home to test your pool chemistry. Right? Or some solutions in the laboratory. Now, if you want to get more expensive, only slightly more expensive, we've gotten pretty good at making handheld pH meters, and this has more to do with electrochemistry that we'll lecture on in the future, but small electrodes that can sense these ions and change voltages, charge carriers, based on the presence of H plus charges or OH minuses. Okay? And so it's sort of measuring the amount of certain charges around and inducing a small voltage that then measures versus a calibrated standard this pH. Okay, so that's a background of what pH is, how we measure it, the relationship between pH and pOH, okay, and then general acids, bases, and neutral solutions overall. In future lectures, we'll get into strong acids and strong bases and start to differentiate them from weak acids and weak bases as we move eventually towards titrations. That'll do it for this lecture. See you next time.